Hello, am I audible? Hello, hello, hello. Hello, hello. Am I audible?
Yes, sir.
So, so we will start this lecture. So, so let me share the screen first. So this is a second course on theory of semigroups. The first course you have already studied in your ninth semester, perhaps. So theory of semigroups, second course, second part. Theory of semigroups. Theory of semigroups and the second part of this. So we will start with the these. We will review this Rees theorem. So Rees theorem. Rees theorem. So this Rees. So this Rees theorem is actually about completely zero simple semigroups. But before defining these completely zero simple semigroups, we will just have an idea of a natural partial order on the set of idempotents of a semigroup. So if you have a semigroup S, so So let S be a semigroup. Let S be a semigroup and you have a set of idempotents and this E of S denote the idempotents set of idempotents of this semigroup S. So by an idempotent I mean that A square equal to A. If A square is equal to A, then I say that A is an idempotent. So these sort of elements, they are called as idempotents of S. So if ES is the set of idempotents of S, then there is a natural partial order on the set ES. Then there is a natural partial order you can define a partial order on the set ES, the set of idempotents of S. You can define in this fashion, defined by, suppose you choose EF, two idempotents in ES, you say that E is less than or equal to F if and only if you have this sort of situation, EF equals FE equals E. So two idempotents E and F, they are related if and only if you have this equation, these equations, EF equal to FE equal to E. Then you can easily see that this is in partial order, means this relation less than or equal to defined here is reflexive, antisymmetric, and transitive. So reflexivity you can easily check. So this less than or equal to relation is reflexive. This is because since EE is E for all E in, for all idempotents E. So this means E is related to E for all E in set of idempotents. So therefore this relation is reflexive, antisymmetric. Now suppose E is less than or equal to F and F is less than or equal to E. Then this implies EF is FE is E, and by this second part FE is EF is E is F, sorry, this second has to be F. Say this equation is 1 and this is 2. So by 1 and 2 E is same as F. By 1 and 2 E is same as F. So therefore this relation is also antisymmetric. Now finally this relation is also transitive. So for transitivity, transitive. Suppose E, F, and G, they are idempotents of S, and you have E less than or equal to F and F less than or equal to G. We must show that E less than or equal to G. So E less than or equal to F implies that, so this implies that EF equal to FE equal to E, and FG equal GF equal F. Then if I take EG, now, now E is same as EF, so I can write it as EFG, but FG is same as F, so this is EF, and again EF is E, so I'm getting EG equal to E. Now let us take GE equal to, again this E is same as FE, so this is GFE, and GF is same as F, so this is FE, but FE is same as E. So what I'm getting here, I'm getting EG equal GE equal E. So if you see the definition of the relation, this implies E less than or equal to G. So therefore, the given relation is a partial order. It is called as the natural partial order. So hence, this is a partial order, on the set of idempotents ES, called the natural partial order on ES. Okay. Now, if S is a semigroup, now the question arises that whether this set of idempotents of a semigroup is empty or non-empty. Now, suppose you have a semigroup S, which is a semigroup with 0. Now, if S is a semigroup with 0, S is a semigroup with 0, then by definition of the 0 element, we know that this 0S is S0 is 0, and 0 square, which is 0, 0, which is 0. 0 is always an idempotent. This says that this is an idempotent, and this says that this 0 is, so 0 is less than or equal to E for all E in ES, because 0 has this property, and this is the defining property of the relation actually. So, and in fact, so this means if 0 is related to every element of the set ES, it means 0 is the minimum element of ES. So thus 0 is the unique minimum idempotent. So thus 0 is the unique minimum idempotent of S. So if S is a semigroup with 0, then with respect to this natural partial order, the 0 element of S is always an idempotent, and it is the unique minimum idempotent. Okay. Now, we are not interested in 0. In fact, we are interested in non-zero idempotents. And those idempotents which are non-zero idempotents and which are actually the minimal idempotents, they are called as primitive idempotents. So let me just give the definition of the primitive idempotent. Okay, so thus idempotents, so definition, the idempotents that are minimal, you know the definition of minimal, the idempotents that are minimal within the set of within the set of non-zero idempotents, non-zero idempotents are called primitive, are called primitive. So a non-zero idempotent which is minimal. Minimal means minimal. Suppose I have y. Suppose x is a partially ordered set and y is a subset of x. So a belonging to y is minimal. Is minimal means there is no element of y that is strictly less than a. So a belonging to y is minimal if for all y belonging to y, a less than or equal to y, sorry, y less than or equal to a must imply that y is same as a. Okay, so this is the definition of a minimal element in a of a subset of a partially ordered set. So x is a partially ordered set, y is a subset of x, and a is some element of y. We say that a is minimal if for every y in y, if y is related to a, it must imply that y is same as a. Means no other element is related to a except a itself. So when I say that an idempotent is primitive, it means that so thus by definition of minimal, primitive idempotents must have this property. Primitive idempotents has the property that has the property that they are minimal within the set of non-zero idempotents. Means what? Means that e less than or equal to f, where f is non-zero, must imply that e is same as f. Or in other words, by definition of this relation, ef equal to fe must imply ef equal to fe equal to f must imply that e is same as f, where f is non-zero. So an idempotent is said to be primitive. An idempotent e is said to be primitive if e is related with f must imply that e is same as f for all f. Or in other words, ef equal to fe equal to e, sorry, e on here it should be, must imply that e is same as f. So this is the definition of a primitive idempotent. And a semigroup is called completely zero simple if it is zero simple and it contains a primitive idempotent. So a semigroup, 1 minute. So thus we have the definition of a completely zero simple semigroup. So a semigroup S is called completely zero simple if S is zero simple, if S is zero simple and has a primitive idempotent, and S contains a primitive idempotent. Primitive idempotent. You know the meaning of a zero simple semigroup. भाई zero simple semigroup तो आपको पता है ना? Yes. Zero simple आपको पता है नहीं? Simple पता है नहीं? Simple. हाँ. Am I audible?
Yes, sir.
Am I audible?
Yes, sir.
हाँ बोलो भाई, मेरी आवाज आ रही है आपको?
Yes, sir.
हाँ. तो जीरो सिंपल सेमी ग्रुप क्या हो गया? एस इज जीरो सिंपल, इसमें दो कंडीशन होगी, इसके कोई प्रॉपर आइडियल नहीं होगा. जीरो एंड एस आर, आपने थ्योरी ऑफ सेमी ग्रुप 1 में ये पढ़ा होगा. जीरो एंड एस और इट्स ओनली आइडियल, पहली कंडीशन ये है. जीरो एंड एस आर इट्स ओनली आइडियल्स. ठीक है. और दूसरी कंडीशन है एस स्क्वायर इज नॉट इक्वल टू जीरो. सेकंड कंडीशन इज एस स्क्वायर इज डिफरेंट फ्रॉम जीरो. और सिंपल के केस में आपके पास सिर्फ यही है कि it has no proper ideals. A semigroup is said to be simple if it has no proper ideals. ये सेकंड कंडीशन नहीं होगी उसमें. लेकिन अगर सेमी ग्रुप विद जीरो है तो उस केस में यू कॉल इट एज जीरो सिंपल इफ जीरो एंड, पहली कंडीशन, फर्स्ट कंडीशन, जीरो एंड एस आर इट्स ओनली आइडियल्स. सेकंड कंडीशन इज दैट एस स्क्वायर इज नॉट इक्वल टू जीरो. तो we say that a semigroup S is completely zero simple if S is zero simple, means S की ये दोनों प्रॉपर्टीज होंगी, and S contains a primitive idempotent. primitive idempotent मैंने आपको बता दिया, वो idempotent जिनकी ये प्रॉपर्टी होगी, E less than or equal to F must imply that E is same as F. Or in other words, EF equal to FE equal to E must imply that E is same as F. So ऐसे सेमी ग्रुप को हम कहते हैं completely zero simple semigroups. Now the question arises that whether these type of semigroup exists or not. So question, do these type of semigroups exist? So this is a very genuine question. We must ask ourselves that whether the semigroups, these completely zero simple semigroups, that we are actually studying, whether they do exist or not. The answer is in fact yes, because our next result says that every finite zero simple semigroup is completely zero simple. Okay, and in fact the Rees theorem says that there are infinite semigroups which are also completely zero simple. But before going to Rees theorem, first I will prove this result for finite case. So this is the first result that we want to prove, and this is proposition. It says that every finite zero simple semigroup is completely zero simple. So every finite zero simple semigroup is completely zero simple. Completely zero simple. तो हमें यहाँ पे सिर्फ एक ही चीज देखनी है कि इसमें परमिटिव आइडेम्पोटेंट है या नहीं, क्योंकि पहली कंडीशन जीरो सिंपल वाली कंडीशन तो आपके पास है, यू आर गिवन दैट इट इज जीरो सिंपल. You just have to prove that it has the property that it must contain a permittive idempotent. So let us see the proof. तो पहले तो हमें दिखाना है कि इसमें नॉन जीरो आइडेम्पोटेंट होना चाहिए, है ना, क्योंकि जीरो तो हमेशा, मैंने आपको कहा परमिटिव आइडेम्पोटेंट मींस it should be minimal among the non-zero idempotents. So first I have to ensure that इस सेमी ग्रुप में नॉन जीरो आइडेम्पोटेंट्स है या नहीं, अगर है तो फिर उनमें मिनिमल है या नहीं है. दैट इज व्हाट वी वांट टू प्रूव. So let S be a finite zero simple semigroup. तो आपने ले लिया फाइनाइट जीरो सिंपल सेमीग्रुप. आपने एक प्रोपोजिशन किया होगा, वो पहले ही सेमीग्रुप थ्योरी के पहले ही पार्ट में किया होगा कि in a finite semigroup every element has a power which is an idempotent. This is a well known result. आपने किया होगा वो पीरियोडिक सेमी ग्रुप के लिए, एंड पीरियोडिक सेमी आपने ये किया होगा इन ए पीरियोडिक सेमी ग्रुप किया है ना ये. in a periodic semigroup in particular, because finite semigroups are always periodic, so in particular for finite also, in particular finite. So in a periodic semigroup or in particular in a finite semigroup, every element has a power which is an idempotent, which is an idempotent. So if you want to see, this is actually proposition 1.2.3 in the book of Howe. मैं हॉवी की बुक को इस्तेमाल करता हूँ, JM Howe. This is our book that we are actually using. So if you see the proposition, इसकी ये proposition है इसकी 1.2.3. See it. So by this proposition, So every element has a power which is an idempotent. So this proposition says. Now suppose first that zero is the only idempotent. हम मानते हैं zero ही इसका एक idempotent है. It has no non-zero idempotents. So then we will arrive at a contradiction. Now suppose 0 is the only idempotent of S. 0 is the only idempotent of S. Then every element is nilpotent. क्योंकि हम कह रहे हैं कि हर किसी ये जो प्रोपोजिशन कह रही है कि हर किसी एलिमेंट की कोई ना कोई पावर होगी जो कि आइडमपोटेंट होगी, लेकिन हम कह रहे हैं कि इधर से हम कह रहे हैं कि जीरो, सिर्फ जीरो ही इसका आइडमपोटेंट है. देन every element has a power which is zero, that is every element is nilpotent. That is अगर हर किसी एलिमेंट की कोई ना कोई पावर जीरो है तो इसका मतलब हर कोई एलिमेंट nilpotent है. That is every element of S is nilpotent. Okay, means what? There you will find some positive integer. So that is, this means there exists a positive integer n, such that s raised to power n, which is equal to s raised to power n plus 1, which is equal to s raised to power n plus 2, which is equal to 0, and this is for all s in S. ठीक है? Now let A be a non-zero element of S. Now let A be a non-zero element of S. देखो भाई, हम यहाँ पे बार बार पीछे वाले रिजल्ट्स का इस्तेमाल करेंगे because this is a second course on semigroup theory, so obviously we would be using the results of the previous course. So I just advise you that पीछे वाले रिजल्ट्स को आप देखें. यहाँ पे अब आप जीरो सिंपल के लिए एक रिजल्ट जीरो सिंपल सेमी ग्रुप के लिए एक रिजल्ट है वो हम यूज करेंगे, एंड दिस इज प्रोपोजिशन 3.1.1 on this book. So proposition 3.1.1, this says that a semigroup S is zero simple. A semigroup S is zero simple if and only if S is S for all A not equal to 0 in S. That is, in other words, that is if and only if for every non-zero elements A and B in S minus 0, you can find there exist some xy in S such that such that x a y is b, ये रिजल्ट है हमारा। इन पर्टिकुलर अब हमने यहाँ पे ए कोई नॉन जीरो एलिमेंट चूज किया है, तो ए के लिए भी ये प्रॉपर्टी होगी। सो बाय दिस प्रोपोजिशन, by above proposition applied to the element non-zero element A, we must have this property. We must have A equal to x a y. Now again फिर a के लिए a की वैल्यू हम सब्स्टिट्यूट करेंगे, तो then I will get it as x square a y square. अगेन फिर हम यूज करेंगे a की वैल्यूज, then I will get x cube a y cube and so on. लेकिन हमारे एस में तो हर कोई एलिमेंट की ये प्रॉपर्टी है कि ये नील पोटेंट है, तो आपको कोई ना कोई पॉजिटिव इंटीजर मिलेगा सच दैट वो पावर जीरो हो जाएगी। इन पर्टिकुलर यहाँ एक्स और वाई की भी कोई ना कोई पावर जीरो होगी, मतलब you cannot continue this process. You will ultimately reach at a stage where you will get a power of x and y which is zero. So therefore, since x and y are nilpotent, we get a equal to 0. Since x comma y are nilpotent, so x raised to power n equal to y raised to power n equal to 0 for some positive integer, n. So this means a equal to 0. But you are choosing a as a non-zero element. You are choosing a as a, क्योंकि a को हमने non-zero element choose किया था, which is a contradiction. Okay. So therefore, our assumption that 0 is the only idempotent is wrong. So the set of non-zero idempotents is non-empty. So which is a contradiction, So the set of non-zero idempotents of S is non-empty. So the set ES minus 0, this set is non-empty. Means you have non-zero idempotents. Okay. So idempotent exists. So thus non-zero idempotent exists. Now we have to show that as there must be a primitive idempotent. Okay. Now by finiteness, the non-zero, the primitive idempotent exists. By finiteness of S, because हमने S को finite माना है. By finiteness of S, non-zero primitive idempotent exists. Non-zero primitive idempotent अगर नहीं एग्जिस्ट करेंगे तो क्या होगा, आपके पास एक इनफाइनाइट चेन एग्जिस्ट कर जाएगी इस टाइप की. अदरवाइज यू हैव E1 greater than, strictly greater than E2, strictly greater than E3, and so on, which is not possible as S is finite. Not possible as S is finite. So what we conclude here, and this proves the proposition, and we get that every finite zero simple semigroup